All right, let's go ahead and talk about valence shell electron pair repulsion, which we call Vsepr for short. It's Vsepr, and so we will call it Vsepr for short. And essentially, what that is, it tells us the geometry that different molecules make. And so, when atoms are bonded together, and you have multiple atoms on, let's say, a central atom, they'll make a certain shape in each depending on the central atom and the number of atoms bonded to that central atom, there's a particular shape that it'll make. And so that's what we're going to talk about today. So the abbreviation Vsepr stands for valence shell electron pair repulsion. And so if you break down what that is saying there, it's the valence electrons repelling each other. And that's really what it comes down to is the electrons within bonds will repel the electrons that are in other bonds. The electrons that are in bonds will also repel lone pairs, and so lone pairs repel bonds, and bonds repel other bonds, and so they repel each other, and so they'll orient themselves in such a way where all of the electrons are as far apart as possible. Vsepr theory states that repulsion between sets of valence electrons surrounding an atom causes these to be oriented in such a way where they're as far apart as possible. So again, the electrons that are in bonds repel the electrons that are in other bonds, or they repel lone pairs, again, to where they all are far away as possible. Now, lone pairs of electrons will actually repel bonded pairs more strongly than bonded pairs. And I'm going to go ahead and talk about this in a moment, but this is really important to know. If you have, let's say, a bonded pair and another bonded pair, those will repel each other, but let's say that you have a bonded pair and a lone pair. A lone pair is going to repel the bonded pair even more, and that actually changes the shape of the molecule. And so something to keep in mind for a little bit here. Now, when it comes to single bonds, double bonds, and triple bonds, we're going to go ahead and say that they all repel each other equally. And so there's no difference in the force of repulsion between a double, triple, or a single bond. Now, Vsepr theory is used to predict the electron geometry and the molecular geometry. Now, we're going to really focus on molecular geometry, but electron geometry is essentially the molecular geometry, except for it includes the lone pairs within that geometry as well. And so when we look at the different models here in a moment, I'll go ahead and talk about that. So when there is more than one central atom, like in the Lewis structures, we had multiple carbon atoms, we talk about the geometry around each central atom. Now, the electron geometry, again, of a molecule describes the arrangements of the electrons, not just the atoms, but the electrons themselves. And so if you take a look at the molecule shape that's on there, it's called T-shape. You'll see the yellow parts to it are actually lone pairs, and you'll see that when we are considering the electron geometry, we consider those as well. If we were to consider just the molecular geometry, we would be only considering the atoms, which makes the T-shape. Now, the molecular geometry is, again, only showing the atoms, not the lone pairs that are around the central atom. So that is an example of a molecular geometry. So I'm going to go ahead and go back here. So if you take a look, that's the electron geometry, which includes the lone pairs within the shape. And then that is the molecular geometry, which does not include lone pairs within the shape. And here are the different shapes that we will come across. This doesn't have everything. We'll go ahead and go over that in a moment. But essentially, all of the different shapes that we will deal with are in your booklet. And so you'll see in your booklet that underneath the, you'll see the highlighted, the page that has this on there, the highlighted molecules are the ones that we'll have to deal with, and we'll go more in depth with that in a moment here. All right, so let's go ahead and go through the different shapes that you'll make. And so what I'm gonna do is I'm gonna show the molecular geometry and the electron geometry, but really what we're gonna focus on is molecular geometry in terms of understanding the shape that they make. So let's say that we add a bonded pair. Oh, also I'm gonna show the bond angles here. Let's say that we add this here. Notice how, first off, this is the central atom, right? The purple is the central atom. And notice how we have two atoms on there. Notice the bond angle as well. If we made this a double bond, notice it's the same bond angle, 180 degrees. And so this here, if you take a look, is called linear. That makes a lot of sense. It's called linear. Now what ends up happening is if we add a lone pair, to the central atom, let's think about what happens here. Now the central atom, if we add a lone pair here, this lone pair will repel these bonded pairs. And so what ends up happening is we have our linear shape. If we add a lone pair there, it will push the bonded pair down and it will make it bent. So if you take a look here, it pushes it down. There we go, and it's bent. So notice the molecular geometry is bent. And so now the electron geometry is trigonal planar, but again, we're just gonna focus on this. So essentially it takes a linear shape and it bends it. And the reason why is because again, these lone pairs are going to repel these bonded pairs. And so what I'm gonna do is I'm gonna take off the lone pair. So there are lone pairs there, but if you don't show the lone pairs, this is the shape that it makes. All right. Let's go ahead and, okay, so when we have two atoms, we either have linear or bent, all right? So those are our two options with two atoms. What if we have three atoms? Okay, well, if we have three atoms, it will be trigonal something. It's gonna be trigonal something. This first one is called trigonal planar. And the reason why it's called trigonal planar is because it's on the same plane. And so if we have three atoms, it's gonna be trigonal planar, or if we add a lone pair to the central atom, so let's think about that. What's going to happen to these bonds? It's going to be similar to the one before. But if we add a lone pair here, what's going to happen is that lone pair will repel the bonds, and it will repel them down. And so, if you take a look here, this here is now trigonal pyramidal. So, trigonal planar, trigonal pyramidal. And the reason why it's called trigonal pyramidal, I'm gonna not show the lone pair, it's still there, but notice how it kind of makes a pyramid. So it makes like a three-dimensional, think about it three-dimensionally, it makes a pyramid. And so yeah, there we go. So that's trigonal pyramidal. So again, our two options are trigonal planar or trigonal pyramidal. Trigonal planar, you add a lone pair, pushes those bonds down, becomes a pyramid. All right, next one. Now we can have four atoms. If there's four atoms, it makes this shape here, and that is called a tetrahedral. That's called a tetrahedral. And the way you remember that is tetra has four. And really it's called tetrahedral because if you connect the atoms, you draw a line between all the atoms here, it actually makes a four-sided shape. That's why it's called tetrahedral. Now, if we add a fifth one, now you can totally add a lone pair here and it'll make this shape, but we'll actually never come across this shape in this class. So we won't need to worry about it, but you can totally do that. So you only need to worry about this one. Now, if we add a fifth one here, notice how we've got this situation going on here. This is called a trigonal bipyramidal. And the reason why it's called trigonal bipyramidal is, again, if you draw a line between all the atoms here, what you'll end up seeing is you'll have two pyramids, one that's the right side up and one upside down, and they're kind of like this. So they're kind of like two pyramids like this. So that's why it's called bipyramidal. And the reason why it's called trigonal is because each pyramid is a three-sided pyramid. So it makes two three-sided pyramids. And that's why it's called trigonal bipyramidal. And then the last one here, we have this here. This is 6 atoms on the central atom, and this makes a octahedral, all right? And so It's like, why is it octahedral if there's 6 atoms? Well, the reason why, again, if you draw a line between each of the dots, or each of the atoms here, you'll end up with an 8-sided shape, right? So you'll end up with an 8-sided shape. And I know it's kind of hard to maybe imagine that, but you'll have one side here, and then you can see you'll have another side here, and so on. And so you have 4 sides on the top and 4 sides on the bottom, which is a total of 8, which is why it's called an octahedral. All right, so I'm going to go through these real quick again. Linear, bent. Trigonoplanar, trigonal pyramidal. Tetrahedral, trigonal bipyramidal, and octahedral. And those are the shapes.